So today's guest is Dr. Tim Duggan from Informatics Matters. He is a CEO and owner. And let me introduce him. So he received his bachelor's and PhD from Oxford University. Then he worked for 10 years for British Biotech. And he worked for OSI Pharmaceuticals for 2 years. And he worked for, before starting his own company, he worked for Chemaxon for almost 12 years. Tim, are you with us? Could you please join us?
Yes, hi Yurii.
Hi Tim.
Hello, everyone.
So before starting our webinar, I would like to run a short poll to see who we have here. So it's basically this. Yeah, could you please indicate your field of interest? Okay. So the poll will finish in 3, 4, 3, 2, 1, 0. I'm gonna close the poll. Thanks everyone for the participation. So I'm gonna come back to the presentation and okay. So before jump into our main topic, I would like to basically remind you what Chemspace is and our major differences from the similar marketplaces. So Chemspace is rather new company, and it was founded in 2015. And the mission at that time, and it is still now, is to expedite research community with the largest offer of small molecules to search and buy. And because most of these molecules, they make on demand, or they're not synthesized, but rather new molecules, we also want to support our users, our customers with high quality services in order to provide them with the updates on their order status and support all the logistics and customs clearance. So we're globally present. We are headquartered in Kyiv, Ukraine, and we have 2 logistics hubs in Latvia. It's Riga, and to support our European customers, and 1 hub in Princeton, New Jersey, to support our American customers. Then we have agents in Osaka, Japan, and we have an advisor in San Diego, California. So as I mentioned, we are a marketplace for small molecules, and we have more than 86 suppliers. All of them, they are world-known vendors. Some of them we just show here on the slide. And with most of them, we have a good communication, good direct contact that allows us to respond quickly to issues, if any, and basically resolve all the problematic situations. So this is how our main page looks like, and I hope you've seen this. And from here you can navigate to all the products we offer, like building blocks, screening compounds. We have expanded space that is over 700 million molecules, and we have compound sets specially designed for all your needs. And if you can find the set here, you can just drop us the line and we'll make the set for you. So yeah, so you can search online using typical search options like exact match, substructure, or similarity, and the search is really fast. So you can do it one by one, or you can do this text search, or you can do the importing file. And then once the search is done, you can select the molecule you're interested in, and basically select the amount you're interested in and proceed with ordering, if this is the only molecule you want to buy from us, or just continue shopping. The database is available online using the mentioned search options. It's also partially available on ChemSpider, SciFinder, PubChem, Zinc15, and Farmit. And we are offering API integration, KNIME nodes, and Punchout site. As I mentioned, we are offering the largest database available to search and buy, and we have number of products. For building blocks, we have over 86 million molecules, 94% of which actually make on demand or in stock, and they are all available with prices. So you can search the compound and order it from us. For screen compounds, we have 58 million molecules in stock, and again, make on demand. Most of them, they are with prices. And we have expanded space, which is actually in a real database with over 720 million molecules available with high success rate in rather short synthesis time. And I'm talking here about make on demand compounds, and I would like to explain more this make on demand concept. It's rather different from what we used to call virtual compounds, because virtual compounds, they are basically molecules that are drawn somewhere and there is nothing basically associated beyond them. So in order to evaluate the synthesis and the price for the virtual compound, you basically need to see that you need to propose a synthetic route to make this molecule from the available reagents, or you need to synthesize those reagents. And that basically influences all the lead time and the pricing. And if you need to make analogues of this virtual molecule, then you basically need to start from the beginning, the evaluation process. For the make on demand compounds, it's slightly different. So imagine we have aldehyde here that is synthesized by a chemist in the lab from the in-stock available reagents. And those reagents are available in decent quantities, and they're rather cheap. So the chemist is done, here we have like 5 steps from this reagent and to make the final compound, and the final compound is actually synthesized in a decent amount. So imagine that chemist can repeat these steps by just using slightly different reagents, again available in a decent quantities from the warehouse. And if you just check the number of reagents that here you see, they are available in more than 50 gram quantities, and basically do the enumeration of the library of this make on demand aldehydes, you can have over 190,000 molecules with known synthetic steps, with known synthetic procedure, and known estimated price, because they're based on the available reagents. You can imagine that it's very easy to find analogs from this within this make on demand space, and again, they are all with price and estimated lead time. These make on demand compounds are good for finding analogs of in-stock compounds to build SAR. You can build a new chemical space. You can try to update your overused stock, or you actually can find you can apply them to Fragment Network, which is implemented by Informatics Matters. And here I would like to give the word to Tim Duggan for further presentation. Tim?
Okay, thanks, Yurii. So what I'll do now is share my screen. So the work I'm going to describe here is based on the Fragment Network, and that's based on the that was conceived by Astex Pharmaceuticals and is described in this publication. that I've got on the screen now. And if you want more details, full details of how the fragment network is conceived and how it works, then reading that paper is a must-do exercise for you. So at the heart of this new FragNet search application that we're launching at the moment to provide a web-based search interface to the Fragment Network, you go to this site, fragnet.informaticsmatters.com, and from here you'll be able to get a login, request a login, and there's documentation and things like that. But the Fragnet search is not the only mechanism of accessing the data in the Fragment Network. One that I'm showing on screen now is the Fragalysis application that is part of the fragment screening program at the Diamond Light Source. And if you're involved with the fragment screening of diamonds, you've probably come across this application. And this provides a 3D context for the fragment hits and the positions in which those fragment hits can be derivatized and extended. But this is a very specialized application based around fragment screening. It's not really useful for more general purposes, and that's what our Fragnet search application is for. It's a much more general application designed to allow us to search and explore the data in the Fragment Network. We also have a interface into Optibrium StarDrop application using their Python scripting interface. So if you're a StarDrop user, you'll be able to run queries from within that as well. But the main application I'm going to show you is the Fragnet search, which is on screen now. And so we've got a fair amount of documentation here already. What I'll briefly do is just sort of go over the concept of the Fragment Network and how it works. I'm just going to use the docs on the website, no slides or anything like that. So the Fragment Network is based around fragmentation of molecules. The example in the Aztecs paper uses 4-hydroxybiphenyl, so I'm going to use this example as well. And basically, the fragmentation happens at derivatization points of rings, wherever you go into a ring, and you can fragment it. As in here in this 4-hydroxybiphenyl, you can fragment it between the rings, or you can fragment off the hydroxyl group. That gives you 3 fragments. You then recombine those fragments in a all but leave out one pattern, and you generate a series of child molecules that are basically fragments of the original molecule. And then you can recurse. If any of these molecules themselves can still be fragmented, like this biphenyl group at the top, that would be then further fragmented, and you end up with a pattern like this. This is the complete fragmentation pattern for 4-hydroxybiphenyl, and we end up with 8 nodes that you'll see here in the black boxes. And it's the data for those nodes, the parent-child relationships, and the molecules themselves. So these are child molecules of the 4-hydroxybiphenyl. That is the data that goes into the Fragment Network database. And so essentially, from a graph or a directed acyclic graph representation, this is what that particular molecule would look like. Obviously, other molecules have their own fragmentation patterns, and many of the fragments might be in common. And this then lets you hop across from one molecule to another to go either from a parent to a child or from a child to a parent. And then you can do transforms by traversing those hops, those parent-child relationships. And an example here would be a simple functional group addition, where we're adding a chloro to the 4-hydroxybiphenyl at the position opposite to the hydroxy. Obviously, the molecule on the left is a parent of the molecule on the right. But we can also do more complex transforms as well if you traverse more than one hop. And so you can end up with things like double additions. Here we're adding the chloro and a methyl group at 2 different positions. You can do substitutions, where we remove the hydroxyl and replace it by something else. And you can even do things like ring replacements. You remove a ring and add back a different ring. And that's the data that is in the fragment network. Why is that useful? Why wouldn't you just use standard similarity search or substructure search or things like that? Well, we describe this in the documentation here about what's novel about it, and basically I think there are two key reasons. One is that fingerprints, the traditional chemical fingerprint type similarity searches just don't work very well for small molecules because not enough bits are being set, and you don't get a good enough similarity signal. And the other really key benefit is this: by traversing these fragmentation patterns, you get a much more chemically intuitive idea of what's similar and what's not. So fingerprint similarity tends to be the sort of computer says yes type similarity, whereas the fragment network gives you something that's far more chemically meaningful. So what we'll do now is we'll quickly show you this in action. So you would typically start with a query molecule, and here let's start with 4-hydroxybiphenyl. As we've already seen that as an example, you can specify a few query parameters. The change in the heavy atom count going from the query to the result molecules, and the change in the number of ring atoms. And you can specify the number of hops. So that is how many relationships, how many graph edges to traverse. One gives you single hop transforms. Two obviously gives you the more complex ones where you can add something and delete something, or add two things and things like that. We'll start by looking at a very simple one. We'll look at the one hops transform. Also, quickly before we execute the search, we have a number of calculations that can be performed on the data, and you can specify those. We'll just stick with these as the defaults. We'll display the log p, and we'll, for interest, display a traditional similarity score to give you to show that what you find with the fragment network you almost certainly wouldn't have found with traditional similarity searching. So we'll execute this, and now we get taken to the results page for that particular search. All your searches are stored in a history here, so you can go and replay. You can go and restore the results, or you can restore the query and then re-execute it with different criteria. But for now, we'll just look at the results of the molecule or the query we just run, and the results get grouped according to the type of transform. And that's what these groupings are here. You'll see the first one is a functional group addition, contains 30 different molecules. And you'll see that all of these results correspond to the same type of transform, a substitution at the position opposite to the hydroxyl. The next one is a functional group addition at a different position. All of these are positions adjacent to the hydroxyl. And so there are a number of functional group additions, obviously, because there are plenty of ring positions you can add something to. And then finally, there's a deletion, where obviously there's only one molecule in this set if you delete the hydroxyl and get back to biphenyl. So that gives you sort of a very simple one-hop transforms. The molecules you get from these sort of searches are fairly obvious transforms. You are probably going to find these through other techniques as well. So let's go back to the query, and this time we'll specify 2-hop transforms. And so we can now go from this 4-hydroxybiphenyl to a child or a parent of that, and then on to another child or parent of that. And here you'll see that you get a much wider range of groupings that are possible. We still get the single functional group additions that we saw before, and we'll skip over many of these. Here we get functional group additions, meaning more than one addition. Which will actually mean 2 additions. So here we've got all the transforms that are substituted at these 2 positions in the query molecule. And there are a number of those because you can combine the different positions. And as we scroll down a bit further, we'll see some other ones. These are still okay. Here's a functional group addition and deletion. So we're adding in one position and we're deleting from the other. But again, all of these molecules conform to the same sort of transform. And if we keep going, we will, and we now see some ring substitutions. So in this case, we delete one ring and add an alternative ring back. What type of rings you can add back is controlled by these query parameters, the change in the heavy atom count and the change in the ring atom count. If you relax those parameters, you can get some much more diverse types of rings. If you restrict those parameters quite tightly, as they are now, you get rings that are roughly the same size as the one that was removed. And there are various other type of transforms. One that's quite interesting here is the linker substitutions. So the link between the two rings is now substituted with something else. And so these are all the molecules that were found in the database that conform to the query criteria and are a substitution of the linker. So as we're going through, we might find molecules that we like, we want to then consider for purchase. So we then add those to the shopping cart. We might go to another query, add that one. I'm just clicking on here fairly randomly, just to build up a shopping cart. And of course, we can go and execute another query. Let's specify this one, and we can go and add some molecules from this query as well. Eventually, we've picked all the ones we're interested in, and we go to our shopping cart. And here in the carts page, you can create multiple carts. So you can have a different cart for different purposes, and you've got we have got a function. The first time you pick some, like these ones I've just picked here, we don't have any availability information for these molecules. All we've got is the molecule that is in the fragment network. We can either fetch them individually, which means going back to our Fragment database, Fragment search database, and picking the availability. Now, there's a key difference here in that the molecules that are specified by the suppliers can include salt information, can include stereochemical information, and things like that. And whereas the molecules in the fragment network are standardized, so the salt information is removed and the stereochemistry is removed. They're achiral molecules. And now we select these molecules that we want to purchase, and we can then filter based on the supplier. At the moment, we've got two suppliers in the database. We've got Molport and Chemspace. We're obviously going to look at Chemspace here. And the Chemspace, once they are shown, we select the ones we actually want. And now at the bottom, we've got a list of either the Chemspace codes, or we've got the SMILES and the Chemspace codes. We want the codes. We'll just copy that to the clipboard, and now we can jump across to the Chemspace site, and we can paste in the codes and run a search on the Chemspace site to find those molecules, and then we can continue through and make purchases, having selected your pack size and things like that. So this copy and paste operation, it would be common between any suppliers. What we're hoping to do is have more direct drill out directly into into supplier sites. So we'd be able to drill directly into the Chemspace website at some stage in the future. But at the moment, as you can see, what you need to do is just copy to the clipboard and then paste into the Chemspace site, and from there on, you're in Chemspace and you can make your purchases. So that's basically it. There's, as I said, a fair amount of documentation already in place, including a user guide. But basically, the mechanism is step one, run your query. Step two, view your results and select the molecules you're interested in. The grouping being the key thing here. That is really what differentiates this. And then go to the cart and select the molecules you actually want to consider for purchase. The actual forms, including the salts and the stereochemistry and things like that. And then jump across to the supplier's site, and then continue your purchase there. So that's it for what I'm planning on demoing. let's jump back to the webinar and see if there are any questions.
Yeah, thank you, Tim. So please, thank you for the nice presentation, and we're looking forward to see your questions. So please type them. So the first question, so do you have all the Chemspace building blocks in the network?
So Yurii, that's really a question for you because you provided me with the data there. We've got about
Right.
5.5 million structures in the database at the moment. So I think you better explain why, how those, which ones you chose.
So basically, as Tim mentioned, we have only 5.5 or 5.6 million building blocks in the Fragment now, and we would like to expand this set to handle all 86 million building blocks. But now it's basically a pilot phase, and I hope we'll just jump to the full set soon. Okay, so I'll read this. Fragment searches will lose parameters, will give an enormous number of hits. Is there a way to post-filter the hits with, for example, a pharmacophoric fingerprint based on the original search query?
Right. Okay, that is a very good question, and it's absolutely right. If you do loosen the heavy atom count and ring atom count parameters, you do end up with a lot more molecules. So that's definitely the case. At the moment, we don't have any way of post-filtering. We do want to add that, and we're actively thinking about what the best approaches are. Yes, traditional similarities, fingerprint similarity probably isn't the right way to go for the reasons that I've already explained. Your suggestion of a pharmacophoric similarity does sort of make some sense, but we're very open to suggestions for what might work well here. We're entering into an evaluation phase, and these are just the sorts of questions we want we want to hear.
Okay, so do you do any sorting in the sets of results to get most common groups first?
Okay, so again, this question came from Richard, and I know in their paper they described how they sort the molecules within the group based on the frequency of those functional group changes. We haven't implemented that at the moment. We're considering doing it, but so it's a bit of an open question. I also think we probably get useful molecules first if we just sort by size, by atom count of the functional group, because typically small functional groups are probably going to be more interesting than the bigger ones. But that is one. The sorting is one bit of the Aztecs publication that we haven't implemented at the moment.
Okay, so do you include multiple tautomers of compounds in the network?
No, we don't. We add the standardized version of the molecule that was supplied by the supplier. So standardization will standardize tautomers to some extent. It would hopefully generate what you might think would be the more common tautomer, the correct one, if any one could be called correct. We don't enumerate them. I think that's an interesting concept, whether we could do that. Obviously, enumerating tautomers has its own issues, though.
And as Richard just commented, heavy atom count is actually a good sorting parameter.
Yes.
Here.
Actually, you notice in the grouping, we display an exemplar structure here. That exemplar structure is the smallest molecule in the group. So effectively, the exemplar is the sorted one. But I think we could very easily add sorting here. I think we should. The the frequency of the functional groups. And the basic idea here is if a functional group of a methyl was much more popular, much more common in the database, that would be sorted higher than other transforms. So that's basically the idea there.
Okay, yeah, thanks, Tim. Any other questions? Okay, as I understand it, the search query itself has to be registered in the database before a search can be done. Is this true with your implementation?
So yes, I think I understand what we're getting at here. The query molecules must be in the database. That is correct. If your molecule is not in the database, you will get no results. Again, the Aztec publication did describe an approach for that, where you fragmented your query molecule and sort of patch it into the database. That we haven't implemented. I think we probably should consider that for implementation.
Okay, thanks. Any other questions?
Okay, so just remind everyone of the site, fragnet.informaticsmatters.com. You need to contact us to get a login at this stage. We're currently in evaluation mode. We're happy to give out logins to allow people to evaluate and give us feedback. Please get in touch if you want to do so.
So yeah, please contact Tim or myself if you have any other questions. And with this, I would like to thank Tim and everyone who attended the webinar.